Alright, we have some practice problems to work through here with simple gas laws, or actually I think these are all going to be ideal or combined gas laws, if I remember correctly. So, the first one here. Calculate the volume occupied by 0.845 moles of a nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 K. So the first question we want to ask ourselves is something changing with this gas, or is this a gas at rest? So is it just, we have a sample and it's just sitting there and we're going to measure something on it, which is the case now. This is a gas at rest. We're not told that the number of moles is changing, the pressure isn't changing, the temperature is not changing. We're just asked to find a property of the gas. And so if that is the case, then we should automatically think ideal gas law. If something was changing, so if the pressure was changing, or the volume was changing, or the temperature was changing, then we should be thinking, okay, can I use one of the simple gas laws, or do I need to use the combined gas law? You should only have to use the combined gas law if all three of those things are changing, if pressure, volume, and temperature are all changing. If it's just two things changing, and everything else is held constant, then we can use one of these. But if three things are changing, then we would need to use the combined gas law. But for our purposes here, we're not changing anything. It is just we have a sample of gas. We want to find the volume. So I'm going to go ahead and do algebra to this first. So if I divide both sides by P, then I will have the volume is equal to the number of moles times the gas constant times the temperature divided by the pressure. So I have my volume by itself. So the next thing I'm going to do is I'm going to go through and make sure that all the values that I'm given are in the proper units, because remember, everything needs to match this. Don't know why I put two dots there. It's liter atmospheres per mole K. So we're given moles, that's good. Atmospheres, that's good, and K. So actually we don't need to change any of these to a different unit. They will all be fine. So that's nice. So we can just take what we have and plug it in. So we have 0.845 moles times 0.0821 liter atmospheres per mole K, so many units. And then that is multiplied by the temperature, which we're told is 315 Kelvin. And all that is divided by the pressure, which is 1.37 atmospheres. Alright, if we check our units, moles cancel, Kelvin cancels, atmospheres cancel. So that leaves us with liters, which is good, because that's what we want for the volume. And so if we go ahead and do that math, 0.845 times 0.0821 times 315 divided by 1.37, that gives me 15.9, let's see, I get 3 sig figs, so actually it's 15.95, but with 3 sig figs that would be 16.0 liters. Now you might have noticed there, in the question they told us we had nitrogen gas. That did not come into play at all. The ideal gas law will work for any gas. It doesn't matter if it's nitrogen gas, hydrogen gas, CO2, water, sulfur dioxide, doesn't matter. All the gases are going to behave the same way. And so it might be an interesting side note to know that the gas we're talking about is nitrogen, but it is not going to change the way that we do the problem at all. Alright, let's do another one here, but this one I would like you to pause the video before you work it out, if you didn't just do that of your own volition on the last one, and try to work this one out on your own given the information in the problem. So go ahead and pause the question, pause the video now. So we're told in the problem, calculate the number of moles. So right off the bat here, we know we're trying to find N of a gas in a, sorry, that's a typo, not a basketball. That should be basket ball. Boy, there's lots of typos on here. Inflated to a total pressure of 24.2 psi with a volume of 3.2 liters at 25 degrees Celsius. All right, so again, we need to figure out, is there something changing? And the answer here is no. We just have gas inside a basketball, and we are trying to figure out how many moles of gas are in there. So if we do our algebra here first, essentially what's going to happen is that RT is going to move over to the other side. So we're just going to divide both sides by RT, which makes all that go away. And we are left with N is equal to PV over RT. Next thing that I would suggest you do is to check your units. And this one, question is not quite as nice to us. In the last one, all the units were already correct. In this case, not so much. So the pressure is in PSI. We need that to be atmospheres. The volume is in liters. That's good. That's what we want. But then the temperature is in Celsius as well. So the temperature is going to be the easy one. That is going to be 298 Kelvin. And how I know that is I'm going to take 25 and then add 273. So remember, that is how we convert from Celsius to Kelvin. We just add 273 to whatever the temperature is in Celsius. And that is 298 in this case. Excuse me. For the pressure, that is one I can't do in my head. We have 24.2 psi. And if you go back and you look at the conversion factor from psi to atmospheres, it is 14.7 psi for every 1 atmosphere. And so this is going to be, let's see here, 1.65 atmospheres. Okay. I think we have everything with the correct units now. So, N is equal to 1.65 atmospheres times, excuse me, sorry about that. I don't think I have the coronavirus. Throat just got really dry all of a sudden. The volume, let's see, that was in the problem. That was 3.2 liters. R 0.0821 liter atmospheres per mole K times the temperature, which is 298 Kelvin. If I check my units here, which there are so many, atmospheres cancel, liters cancel, Kelvin cancels, leaving me with moles, which is good. And if I do that math, 1.65 times 3.2 divided by 0.0821 divided by 298. That is 0.215 moles. So, if you have a basketball that you like to play with, it probably has about 1/5 of a mole of gas in it. Because most basketballs are, they're not just atmospheric pressure, well, not most, all inflated anyway, basketballs. If you had just 1 atmosphere of pressure in your basketball, it would not bounce at all. That would be a flat ball. That would be the same as if you just, poked a hole in the basketball, because that would have 1 atmosphere of pressure in it. All right, last one here. So again, I would encourage you to pause the video and try and work this one out on your own, and then after you finish that, come back and unpause to see how I work through it. Alright, so the question asks, what is the pressure of 1.44 moles of a gas in a 2-liter cylinder at 25 degrees C? So, we're trying to find pressure. Once again, nothing is changing here. Oops, I put that in the wrong. It's not technically incorrect, but I'm going to go ahead and write it the way that we're used to seeing it, nRT. I want the pressure by itself, so I'm going to divide both sides by the volume. So the volume here is just going to go away. In is 1.44 moles. The volume we're told is 2 liters. And then we're once again told that the temperature is 298 Kelvin. We're not actually told that. We're told it's 25 degrees C, which is the same that we had in the last problem here. So it's 298 Kelvin. So we have all we need, actually. Really, the only thing we had to change there was that temperature. So the pressure is 1.44 moles times 0.0821 liter atmospheres per mole K times 298K divided by 2 liters. Sorry, my 2's don't look very good. So, liters cancel, moles cancel, Kelvin cancels, leaving me with atmospheres. And if I do the math here, 1.44 times 0.0821 times 298 divided by 2, I have 17.6 atmospheres. It's a decently high pressure. That's pretty high. Alright, I think we're going to leave it there for this video. In the next one, we're going to pick up and talk about mixtures of gases and how we deal with a group of gases where we do actually care how much of one gas we have versus how much of another gas that we have. And we'll use Dalton's law to do that. Alright, I'll see you in the next video.